Hello everyone, I'm Ziyuan and this is a video presentation of my final year project titled Measuring Energy Consumption at Method Level for Deep Learning Frameworks. As computers become more powerful and as more data become available, deep learning models have become more accurate and more people are studying and using deep learning in both industry and academia. Deep learning has brought about innovations and improvements in many fields such as education, medicine, and transport. To achieve better performance, there has been a trend in deep learning to develop increasingly sophisticated and complex models. In fact, it has been found that the computations required for deep learning research have increased by more than 300,000 times from 2012 to 2018. And in terms of the number of parameters of deep learning models, there's an increasing trend as well. For example, the popular language model, GPT, which is based on deep learning, had 117 million parameters in its first generation, which was released in 2018. The second generation, released in 2019, had 1.5 billion parameters. And in 2020, the third generation with an unprecedented 175 billion parameters was released. With the increased parameters and computations required in deep learning models, it comes as no surprise that the energy consumption resulting from deep learning has been increasing rapidly as well. Not only is such a trend financially costly, it is also environmentally unfriendly. In addition, the lack of energy efficiency also makes deep learning inappropriate for use in end devices with limited battery life like smartphones and Internet of Things sensors. Our ultimate aim is to reduce the energy consumption associated with deep learning, but we need information to guide deep learning practitioners to building more energy efficient deep learning models. We believe that one good way to achieve this is to make energy consumption information available in the documentation of popular deep learning frameworks like TensorFlow and PyTorch. And for these deep learning frameworks, our research have shown that their documentation is most readily available at the method level, as they provide details about the usage of each method. Thus, it makes sense for energy consumption measurements to be provided at the method level as well. However, as yet, no studies have measured the energy consumption of individual methods within deep learning frameworks like PyTorch and TensorFlow. Thus, this highlights the need for gathering energy consumption measurements for individual methods within deep learning frameworks to assist developers in writing more energy-aware deep learning programs. Moving on to the methodology of the project, a client-server architectural setup was devised for measuring energy consumption at the method level. In this setup, the client performs source code analysis on the client-side program, which is a piece of deep learning code written in Python using frameworks like PyTorch and TensorFlow. The client uses the information retrieved from the client-side program to generate API requests for each method of the deep learning framework under investigation. The requests are sent to the web server constructed using the Flask framework. These requests are received by the server, which uses the contained data to reconstruct the method for execution on the server. As the method is being executed, energy measurement operations will be carried out on the server as well. To elaborate on what happens in the source code analysis stage at the client's end, we make use of this sample client program as an example. First, the client program is parsed to produce an abstract syntax tree, also known as an AST. This slide shows a visualization of the AST. With reference to the example of the client program, the first line, where TensorFlow is imported, is represented by the blue portion of the AST, and the second line, where the result assignment from running a method takes place, is represented by the green portion of the AST. After the AST is obtained, it is visited for relevant information to be extracted. For instance, visiting the import node retrieves the import string import TensorFlow STF. The method signature is also retrieved. For the positional arguments, a list is produced, and for the keyword arguments, a dictionary is created. As the client then needs to send API requests containing the extracted information to the server, the AST object needs to be manipulated and rewritten to achieve a transformation in the source code. A general function that sends post requests to the server will be added to the client program. The method calls under investigation will then be replaced with calls to this general function. Moving on to the server, this table shows the platform details where experiments are conducted. To conduct energy consumption measurement for CPU and RAM, the perf command line tool was used. An example of how the output file looks like is shown here. The start time is recorded, and performance monitoring events that make use of Intel's running average power limit reports the CPU and RAM energy consumption, which are given in units of joules. Readings are taken at regular intervals, as seen in the first column, which shows the time elapsed in seconds. And for GPU, we make use of NVIDIA's System Management Interface, also known as NVIDIA SMI. It provides detailed information about the real-time status of the GPU, including the power draw, which is what we are interested in. This is what the output looks like, with the timestamp information as well as the power consumed in watts. To create a standalone web server, the Flask web framework was used. Our Flask application only has one root that listens for post requests. This diagram shows the processes that happen within the server. To check whether the server is in a stable state, the output files from Perf and NVIDIA SMI are read and parsed to produce energy opt measurements. The standard deviation and mean from the last 50 data points are taken to calculate their ratio, also known as the coefficient of variation. For the server to be considered stable, the coefficient of variation must be less than 150% of a reference, and this must be true for CPU, RAM, and GPU. If the server is not yet stable, it sleeps for 0.5 seconds before the check procedure is looped. If a stable state is not reached within 30 seconds, a timeout error is raised. The result of the code transformation of the client program is shown here. There's the addition of a new function, custom method, that sends a post request to the server with serialized data containing the details of the method under investigation. The original method call is also replaced with a call to custom method. In conclusion, this project presents a novel approach to collecting energy consumption readings at a method level granularity in the context of deep learning. However, this approach is also generalizable to use cases beyond deep learning. And this is the end of my presentation video. Thank you.